In the early summer of 1783, a fissure tore open across the Icelandic landscape, stretching for miles through hardened earth. From it rose vast columns of fire and gas, pouring into the atmosphere with a force that would not remain confined to the island. Within weeks, a haze spread across Europe, dimming sunlight, choking fields, and unsettling entire populations. Crops began to fail. Livestock weakened. In distant regions that had never heard of Laki, people fell ill under a sky that no longer behaved as expected. What began as a volcanic event in a remote corner of the North Atlantic became one of the most far-reaching environmental disasters of the 18th century. The eruption, now known as the Laki Eruption, began on June 8, 1783, in southern Iceland. Rather than a single volcanic cone, Laki consisted of a chain of craters extending approximately 27 kilometers. This type of eruption, known as a fissure eruption, allowed magma to escape along a long crack in the Earth's crust, producing sustained outpourings of lava and enormous quantities of volcanic gases. Over the following 8 months, the eruption released an estimated 14 cubic kilometers of basaltic lava, covering vast tracts of land and permanently altering the Icelandic terrain. The scale of gas emissions proved even more consequential than the lava itself. The eruption released massive amounts of sulfur dioxide, hydrogen fluoride, and other toxic compounds into the atmosphere. These gases combined with moisture to form a dense, dry fog, often described in contemporary accounts as a blue haze. This haze did not remain localized. Carried by prevailing winds, it drifted across the North Atlantic and into mainland Europe, where it lingered for months. In Iceland, the immediate effects were devastating. The toxic fallout settled onto grazing lands, contaminating grass and water supplies. Livestock, particularly sheep and cattle, ingested fluoride-laden vegetation, leading to widespread poisoning. Contemporary records indicate that approximately 50 to 80% of Iceland's livestock perished in the aftermath. For a society heavily dependent on pastoral agriculture, this loss was catastrophic. The human toll soon followed. With livestock dying and crops failing, famine spread rapidly. It is estimated that roughly 1/5 of Iceland's population, around 10,000 people, died as a result of the eruption and its consequences. Many succumbed not directly to volcanic activity, but to starvation and disease brought on by the collapse of the food supply. The event became known in Icelandic history as Mjöharandin, or the hardships of the mist, a term that reflects the central role of the toxic haze in the disaster. Beyond Iceland, the effects were more diffuse but no less significant. In June and July of 1783, reports began to emerge across Europe describing unusual atmospheric conditions. In England, observers noted a persistent dry fog that obscured the sun and gave it a reddish hue. The haze was accompanied by a sharp, sulfurous smell, and many reported irritation of the eyes and throat. Similar accounts appeared in France, Germany, and Scandinavia. The summer of 1783 became one of the hottest on record in parts of Europe. The haze trapped heat near the surface, contributing to unusually high temperatures. Rivers ran low, and agricultural systems came under strain. While heat alone does not account for widespread mortality, it compounded existing vulnerabilities, particularly among the poor and elderly. Medical understanding at the time was limited, and the connection between the haze and health effects was not fully understood. However, parish records and mortality data suggest a noticeable increase in deaths during the summer months. In England, excess mortality has been estimated in the tens of thousands. Respiratory distress, aggravated by the polluted air, is believed to have played a significant role. In France, the haze coincided with broader agricultural challenges. The late 18th century was already a period of economic strain, and the disruption caused by the unusual weather patterns contributed to rising food prices. While it would be an overstatement to attribute major political events directly to the eruption, environmental stressors such as these formed part of a complex web of conditions that affected European societies in the years leading up to the French Revolution. The atmospheric effects of the eruption were not limited to the summer. As the year progressed, the injected particles and gases influenced weather patterns on a broader scale. The winter of 1783 to 1784 was notably severe in many parts of the Northern Hemisphere. Rivers such as the Thames in England and the Seine in France experienced extensive freezing. In North America, reports describe prolonged cold and heavy snowfall. The The mechanisms behind these climatic effects are now better understood. Sulfur dioxide released during the eruption formed sulfate aerosols in the atmosphere. These particles reflected sunlight, leading to cooling at the Earth's surface. At the same time, they altered atmospheric circulation patterns, contributing to regional extremes in temperature and precipitation. The Laki eruption stands out not only for its scale, but for the way it demonstrated the interconnectedness of environmental systems. An event in a sparsely populated region of Iceland had measurable consequences across continents. In an era before industrial emissions became a dominant factor in atmospheric chemistry, this natural event provided a stark illustration of how large-scale releases of gases could influence climate and health. Contemporary observers attempted to make sense of what they were witnessing. In England, the natural philosopher Gilbert White wrote detailed descriptions of the haze and its effects, noting the unusual behavior of the atmosphere. In France, scientists and physicians recorded similar observations, though explanations varied widely. Without knowledge of volcanic gas chemistry or atmospheric transport, many struggled to identify a clear cause. Communication limitations of the time meant that the connection between the Icelandic eruption and the European haze was not immediately recognized. It was only later, through the comparison of timelines and reports, that a clearer picture emerged. Today, ice core data and geological studies have confirmed the scale of the eruption and its far-reaching impact. In Iceland itself, recovery was slow and uneven. The loss of livestock and the degradation of land had long-term consequences for agriculture. Some regions remained uninhabitable for years due to lava coverage and soil contamination. The social fabric of communities was strained as families faced displacement and hardship. The Danish crown, which governed Iceland at the time, provided limited assistance. Relief efforts were constrained by distance, logistical challenges, and the broader economic context. As a result, many Icelanders were left to cope with the aftermath largely on their own, relying on local resilience and adaptation. The eruption also left a lasting mark on scientific inquiry. It contributed to early discussions about the relationship between volcanic activity and climate. While a comprehensive understanding would not develop until much later, the observations recorded during this period became part of a growing body of knowledge about Earth's systems. In modern terms, the Laki eruption is often classified as one of the most significant volcanic events of the last millennium. Its sulfur dioxide emissions are estimated to have exceeded those of many well-known eruptions, including some in the modern era. The event is frequently studied in the context of volcanic forcing of climate and its implications for both natural and human systems. The health impacts observed during the eruption have also informed contemporary research. Studies of historical mortality patterns provide insight into how air pollution affects populations, particularly in the absence of modern medical interventions. The Laki event serves as an early example of large-scale atmospheric pollution and its consequences. Despite its significance, the eruption is less widely known than some other historical disasters. This may be due in part to its diffuse nature. Unlike events characterized by a single moment of destruction, the effects of Laki unfolded over months and across vast distances. Its impact was cumulative, affecting agriculture, health, and climate in ways that were not immediately visible as a single catastrophic event. Yet its legacy endures in multiple forms. The physical landscape of Iceland still bears the marks of the lava flows. Historical records preserve the experiences of those who lived through the hardships of the mist. Scientific studies continue to draw on data from the eruption to better understand the interactions between geology, atmosphere, and human society.